Okay, good afternoon, everyone. Thanks for staying out until the very end for my talk. Today, I will try to answer this seemingly simple question, which turned out not that simple. Like, does higher refractive index mean higher gloss? So when we talk about refractive indices, so when the light hits the boundary of the two media with mismatching indices of refraction, it is partly reflected and partly refracted and is transmitted to the second media. And the amount of reflected light depends on the differences of the two refractive indexes and also the angle of incidence. So for a given incidence, then if the difference between two refractive indices is larger, the higher amount of light is reflected. And oftentimes this is simplified to the concept that the higher the reflected amount of light, higher the gloss. But this doesn't work in this straightforward way when it comes to perceptual gloss. So here with gloss, I mean perceived gloss, what is perceived as glossiness by the human visual system. So, and another simplification that we often see that gloss is often simply used synonymously with specular reflections, which from a perceptual perspective is not also the same. So there are believed to exist a broad range of image cues or visual cues that help us our visual system to perceive something as more glossy than there are other materials, or to distinguish between glossy and matte. So in addition to specular reflections, so there are some image regularities, for instance, the distinctness of image, how clear the image is, and on the other hand, when it gets rough or surface geometry changes that blurs or makes it less distinct, it appears less glossy, or for instance contrast gloss, where darker materials appear glossier than the lighter ones because of higher contrast, the reflections of the surroundings stand out more, and so on. It depends not only on the material properties, the perceived gloss, but also object shape. For instance, you can see here that this is made of the same identical material, but because of its relatively simple shape and curvature, we can use spheres if they are smooth enough as mirror reflectors of the environment, while loosey shape made of the same material cannot be used as a mirror because its surface geometry and shape does not permit to see these clear reflections of the environment. So to get back to the refractive index, as you can see here, when we increase, if we fix the outer medium, so in this case we assume it's vacuum, fix the N1 to 1, and vary the refractive index of the object's material itself. So if we have 1.1, then 1.33, that is approximately that of water, 1.5 and 2.41 to the diamond. As you see, it appears more and more glossy, and this one looks the glossiest among those four, and it is almost like appears like a mirror. But on the other hand, we can notice that when the higher portion of the light is reflected from the surface, the smaller portion is refracted and the smaller portion penetrates a subsurface. And in earlier work, we showed that subsurface scattering, even though it is often neglected when studying glossiness perception, actually contributes to perceived gloss. So here the refractive indices are fixed, surface roughness. So what happens at the surface scattering is identical, but what makes difference in terms of perceived gloss is subsurface scattering. So interestingly, for spherical materials, we observed that when we increased albedo, it decreased in glossiness because the light that was backscattered from the subsurface decreased the contrast and the reflections were less noticeable. But for this kind of complex shape, it was actually the opposite because this highlights that are actually resulting from the subsurface scattering because of high albedo were mistaken for reflections, and this material, for instance, was considered glossier than this one, even though they reflect same amount of light from the surface. So this can be one of the mechanisms how additional mechanisms that how refractive index can affect perceived glossiness via translucency. So if we have lower refractive index, more light penetrates into the subsurface, and then depending on the scattering there, it may affect perceived glossiness. So we studied this with psychophysical experiments. We generated 105 images in total of spherical objects. So we designed by some trial and error after some visual inspections, 21 material groups that came in 3 different alphas, surface roughness levels, also 3 different extinction coefficients, and 3 different levels of albedo. And then each of those 21 were rendered with 5 different values of refractive index. So in each group, there are 5 images that vary only in refractive index and nothing else. And then we conducted 2 psychophysical experiments. The first one, we started from simple pair comparison, because we noticed in previous works that usually pair comparison tasks are a lot easier and observers are more consistent when they are asked simply, okay, these are the 2 objects, which one is glossier, left or right? While magnitude estimation is more subjective and observers take a larger amount of effort to scale the magnitude of glossiness on a given scale within a particular range. So we started with pair comparisons, and first we wanted to fix all other parameters, so everything was identical, and we compared only images that differed in index of refraction. So everything else was the same. So for the comparisons were made within each material group, while in the second one everything was scaled, so all images were used on the same scale. We had 17 observers, and let's start with the analysis of the first pair comparison experiments. We conducted very simple frequency analysis. So we thought of 2 scenarios. One is that is hypothesized and expected and would be more intuitive, that higher the index of refraction, higher the gloss. So the observers should typically select the image with higher index of refraction. And the case B, when this assumption is violated. And in most cases, we noticed that yes, observers picked the images with higher refractive index, but there were some exceptions where it was pretty abundant, the cases where the opposite was true. And if you have a look at the materials that exhibited such behavior, you will see 2 trends. One is that all of those have very rough surface, and they have either a very low extinction coefficient, or if extinction coefficient is relatively larger, they have a relatively higher albedo. So let's start with the latter case, and if we have a look at the z-scores, so in the horizontal direction, refractive index increases. So here the main result or observation was that when it is very rough, refractive index needs to be increased very much actually to make a visual difference in gloss, because they look all of them look very matte, and when the refractive index difference is very large, only then it makes a difference. And when its albedo is high, it may happen that because of higher subsurface scattering, this may produce slightly lighter shade than the other, but overall their glossiness doesn't differ a lot. But there is an even more interesting case which had almost like more than 40% of the cases where the ones with lower refractive index were considered glossier. And this was a material with 0 extinction coefficient, so the scattering was happening only on the surface and it was perfectly transparent inside. And if we compare these two cases, one is that conforms to our expectation. When we increase refractive index, it monotonically increases in terms of perceived gloss. While for this material, I will show a close-up images in a while. We see that it starts from very low glossiness, but then its glossiness increases, and at some point it starts to decrease again. So what can be the explanation for this one? So if we have a closer look here, we see that for this material, the highlights, it's smooth, and the mirror reflections become sharper and more, they stand out more, they become brighter. While for this one, actually at some point for a given refractive indices, so on the surface it produces hardly any glossiness cues because it's very rough. But what actually it seems to be affecting observers' decisions are these internal caustics. So when the certain amount of light penetrates into the subsurface, it's bent because of the mismatching indices of refraction, and because of the shape of the sphere, it's focused on the other edge of the object, and this internal caustic pattern is produced, which is seemingly affecting observer judgment of glossiness. And then when we have a higher refractive index for these materials, then little light manages to get to this point. So as you see, like the left part, because of the reflections, is lighter than here, but then these cues here disappear. Then we ran some statistical tests. Of course, index of refraction, considering like the most materials, had a significant effect on mean opinion scores for magnitude estimation. So in this experiment now we already have the magnitudes for individual images on 0 to 100 scale. But interestingly, when we tried to calculate like correlation between index of refraction and mean opinion scores for this peculiar material, it was negative, while for the majority it was the strongly positive correlation. To plot mean opinion scores from the magnitude estimation against indices of refraction, we see that there are three groups that stand out very clearly, and this was expected because the surface roughness has the strongest impact on perceived gloss among all. So the curves with blue correspond to the smoothest objects, then the orange ones second smoothest, and the green ones correspond to the roughest objects among all. And as you see, there is a very obvious separation based on the roughness levels. But then another interesting thing is that smoother the surface, the steeper is the slope. So when it's smooth, we can clearly see the reflection of the environment. So its brightness or sharpness, how much it stands out, makes larger impact. While when it is very rough, then the index of refraction makes smaller and smaller impact. Even if we fix everything else and just make the surface a little bit rougher, how much index of refraction matters changes between these two roughness levels. And here we can have magnitudes of these two interesting cases that we showed before, similar ones, where we have increasing magnitude, but of course at some point when it reaches almost like maximum, it becomes almost perfect mirror, then it doesn't change much. While for this material, overall, because of its rough surface, its glossiness does not seem to reach high levels, but these ones have still slight increase in comparison with this one. To check exactly what cues change in terms of like image cues among these different scenarios, we calculated pairwise differences, pixel-wise differences between different versions of the material. And for the one which had like monotonically increasing glossiness, as you see, the highlights or the reflection of the environments stands out more and more, while here in that specific exception, we see that it really depends. The ones with higher refractive index have more intensity, lighter side on the side of the incidence of illumination, while the ones that was considered the glossiest has most intensity that was already shown in the previous examples on the other side. And another question is like, what are exactly image statistics that can be useful for predicting visual gloss? So there have been multiple suggestions. One very popular one was that asymmetry of luminance histogram can be correlated with perceived gloss, skewness or kurtosis. So we isolated the luminance channel and calculated the mean, standard deviation, skewness and kurtosis of the luminance histogram. And we see that standard deviation is the one most positively correlated with index of refraction, while for instance for the mean there is no correlation at all. But again, the only one that has zero correlation between index of refraction and luminance histograms standard deviation is this one particular material. So the limitations and future work. So one limitation that was also the limitation of the previous study where we found a link between translucency and gloss is that we worked in the lower dynamic range. So in a high dynamic range scenario, we may see that some areas that may become saturated. Actually, we may discern more details. So it is important to try this on in HDR. Second very important aspect is to try other shapes, because as I showed in the beginning, so this was just the first step tried on the spheres, but of course the sphere's curved shape makes it act like a lens and focuses envelope of light to form these caustics, but it may have completely different effect on Lucy. So there can be different areas where we may appear in highlight or not. And other illumination conditions, whether these observations extend to other illumination conditions should be an open question for future work. And in simple terms, this one very particular exception that was observed in this data set, it is worth exploring to what extent this generalizes. So is this material behaving this way for all shapes, for all illumination conditions, or maybe not, maybe just for spheres that this strange thing is happening. So in conclusion, for most materials, as it was expected, monotonically increasing, its glossiness, perceived glossiness is monotonically increasing with index of refraction, but this is mostly for smooth objects where we can clearly see the reflection of the environment. When we make it rough, the role of refractive index decreases, and they usually look more or less equally matte, and it's difficult to judge their glossiness. And very interesting scenario is when we have a high degree of subsurface light transport and it's like nearly transparent material, then this strange thing happens. So final message is that higher refractive index may not always and necessarily mean higher perceived gloss, but to what extent it means higher gloss and in what cases this assumption fails needs further investigation. Thank you very much for your attention.